Hello guys, welcome back to our next lesson. This session will be about the chapter solid states. So let us start with the chapter without any delay. So the basics you must have learned about the amorphous and the crystalline solids, and about the isotropy and anisotropy in the nature of the properties, right? Where like if they have so there are some solids which have similar structures in the same in all the directions, right? And there are others which do not have the similar structures in the same directions. So like if you have cubic cubic cells, they'll have always a constant property going on across their own solid because of the similar structure throughout. But as we go for diamond is a structure where you won't find the similar unit properly atoms placed exactly at all the positions, so it will not follow uniform property. So these are the basic things. So let's start with the important ones. So the very first thing is to know about the unit cell, right? You know what a unit cell is basically. So in a lattice, so when you're talking about solid state, we're talking about basically first of all the ionic solids. In the ionic compounds, what happens is, so the ionic compounds, the atoms form a lattice structure. Now what is a lattice structure? So it's simply arrangement of all the atoms together because of the bonds of like electrovalent bonds or the metallic bonds, right? So basically the structures look like, so for a lattice the structures are like there are lots of atoms holding together, and this is just a 2D view. So if I extend it behind, there will be atoms behind this, right? And then there will be more atoms behind it, and it's like a big huge lattice, right? This is called Bravais lattice or space lattice. Now, what is a unit cell is basically it's a very small is the smallest we can say it's a smallest part of the lattice itself. So if I take we can consider any kind of unit cell, by the way. We can consider a square if you want to go for a 2-dimensional, we can go for square or rhombus. But if you want to go for a 3-dimensional unit cell, we go for like a cubic or a cuboidal or rhomboidal or hexagonal. There are many types of unit cells, and you can also define a unit cell by your own choice and own discretion. So that is not the question what kind of unit cells can be. So let us understand about some of the unit cells. All right. So the first and the simplest of the unit cell. So what we learned is a unit cell is basically a subdivision of the lattice itself. All right, is the smallest cell, we can say, the smallest cell, right? So the lattice basically can be divided into different types of unit cells. Like we have a simple cubic. Now we're talking about lattice. That's a 3D structure. A lattice is a 3D structure. So obviously our unit cells will also be 3-dimensional, correct? So in that view, we can say that the unit cell can be as simple as a cubic unit cell. Now what will be a cubic unit cell? We know this cube, right? So on this cube, if I put atoms at each corner, this will be called as a simple cubic unit cell. All right. So here we'll have all the lengths, the edge lengths. These are known as the edge lengths. What is an edge length? So the edge length is basically the distance between two consecutive atoms. That is the edge length of the unit cell. All right. They will always be same, as you know, for a cube it is. And then also about the angles will also be equal to 90 degree, right? So then there is a there are other this is a cubic unit cell. More important one, another important one is hexagonal cubic cell. So what does a hexagonal unit cell would look like? It would be a hexagon. simply. Yeah. Yeah, more or less. So this is a hexagonal unit cell. Now the atoms will be kept here, 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 right? So these kind of unit cell would be a hexagonal unit cell, right? So all the angles would be 120 degree as it's a hexagon, and the sides will be equal. Here these sides will be equal, correct? Now, so these are just the unit cells, but in unit cells then there are further types of crystal structures. So like for the cubic, simply we can get a simple cubic, body centered, and face centered for the first three. Simple cubic structure is the one that we just studied. So these are just types of crystal systems, right? Now when we talk about unit cells, so unit cells can be of many different types. So like for a simple cubic, we have the simple structure of atoms placed at the corners of the cube. So when the atoms are placed at the corner of a cube, now imagine your hall, right? On the hall, if I place at each corner, there are 8 corners, right? At each corner, if I place an atom, or if I place a ball, so will the whole ball be visible from inside the room? No, right? Because it's basically you can't see the whole ball, because only a part of it will be visible inside the room. The other part will actually be outside. So this part that I'm talking about right now, so this part would be outside, whereas only a very small part, this part, would be inside, right? So if I actually see, look at this now, right? So at this corner we have just 1/8, 1/8, yes. So at this corner, at one corner, we can only have 1/8 of the contribution of the whole atom that is placed, or the ball that is placed, right? So total number of atom that one cubic unit cell will contain how much? Will be 8 into contribution. That contribution is 1/8. So total will be 1. Right. So now next we have is body centered. So now in the body centered, what we have is, so obviously we have the atoms at the corner, as well as the name suggests, there is one more atom placed at the center. So now in this, how many number of atoms do we have? So as we know, the ones that are placed at the corners will have a contribution of 1/8. So there are 8 atoms with 1/8 contribution, and then there is one atom with a complete contribution, giving us total 2 atoms in a body centered unit cell. Now, and thirdly, we have a face centered unit cell. Now the face centered unit cell, in the face centered unit cell, we have, other than the cubic ones, they are always present because the cubic structure, right? In the cubic system, we have 3 different kinds: simple cubic, body centered, and face centered. In the face centered unit cell, so how many faces do we have? We have 6 faces. So 6 faces will have 6 atoms placed at the center, like here and here. That there is here and here, and then there is on this face here, and the face which is exactly behind. correct? And how much contribution do they have? They'll have half a contribution. So basically I'm just putting one ball on the wall of the room, so what I can see is only half a ball, not the whole ball, hence the contribution is half, correct? Half at the face. So how many total number of atoms now we have here is 8 into 1 by 8, which is at the corners, and then we have 6 into 1 by 2. Total 4 atoms in a face centered unit cell. Alright, why is this important? We'll see why this is important. There's one more arrangement of unit cell that is generally not taught, but yeah, we can just remember it. It's called end centered. Now end centered is basically again a cubic unit cell which is like face centered, but with only one exception, that is obviously it will have 8 atoms present at the corners, but end centered will have only 2 atoms present on the faces, but only 2 atoms on the opposite faces. So it can be the top and the bottom face, or the side faces left and right, or the front and the back, any 2 basically. So I'll just make it here and here. So this kind of structure would be a end centered unit cell. So it will have total 2 atoms. Why 2 atoms? 1 from the corners and total of aggregate of 1 from the end faces. Alright, so total 2 atoms. This is just like body centered in the terms of number of atoms, not in the terms of structure. So this was about the different kind of structures that can be formed. Alright, next, so let us understand how these structures help us in understanding basically the fractional space that these atoms cover. Okay, so next we can talk about the packing fraction. Now when we talk about the packing fraction, what we're talking about basically is that, okay, so there are atoms in we are trying to fit a circular thing into a cubic unit cell, right? So here we have a unit cell. Now what we are trying here is we are trying to fit a complete circular thing into this unit. Now we know that a circle, a cube, a sphere cannot be exactly fit into the cube, right? So what happens is, so there is a lot of space which is left inside it. Alright, so let us consider this unit cell with the edge length of A. Okay, and here I have some atoms placed on this and this point, one here and the other here. Okay, similarly we'll have one here and the other is here. So if I look at from the top, the arrangement will look like this, correct? So as you can see, there is void here. Similarly there will be a lot of void. So what happens is, so when we try to calculate packing fraction, what we find is the fraction of space that is covered by the spheres that is volume of sphere into its number of atoms aggregate upon volume of unit cell. In our case this is a cubic unit cell, so we will be taking A cube since the length is A, so the volume of the unit cell will be A cube. Whereas on the top, we know the volume of sphere. What is the volume of sphere? 4 by 3 pi r cube. Now what is this r? This r is basically the radius. This radius of the sphere. But as we know that they are not all the so we know that these number of spheres are not exactly fitting inside the cube. So what we want basically is the packing fraction inside the cube and not outside it. So we'll have to consider the coordination number also. The coordination number basically is the number of atoms that are actually inside the cube. As we calculated in the last sheet here, as you'll be able to see now. So in the cubic there is only one cube, right? This we are calling n. This is the coordination number. For body centered and for end centers we have 2 atoms effectively. For face centered we have 4 atoms effectively. So similarly, basically we are calling this as our coordination number and we are multiplying it this. So this comes out to be as our packing fraction, and in this way we can calculate how much amount of space in the lattice is covered by the atoms and how much is free. Now if we calculate the spaces, what we find is that generally the highest that comes out for is hexagonal and face centered, right? Now for a simple one, for simple cubic, it generally comes out to be around 52%. Alright, whereas when you talk about body centered, this goes to 68%, but face centered or hexagonal, they generally have an amount of 74%. Now when the packing fraction is high, this basically shows that there are more atoms present inside that cube. Hence we generally find that more and more unit cells are basically present majorly in the face centered unit cell form or the hexagonal unit cell form, right? If we talk about the hexagonal, so if we calculate how many atoms are present inside it, but we should also take care of the space that is being covered, because it's a bigger structure, it will be covering more space, right? So here the contribution of these 12, 1 2 3 4 5 6 on the top and 1 2 3 4 5 6 on the bottom, this 12 is 1/6, right? Whereas there are 3 atoms which are present inside, exactly in between here, 1 2 and 3, and they are exactly in the body. So one-sixth and 3 atoms, 1 2 3, yeah, that is in the center, right? Body center. So this gives us the amount of the atoms present in the hexagonal unit cell. But what happens is, this also the volume of the unit cell is also increased. Although the number is increased, but volume was also increased, due to which the packing fraction comes out to be approximately 74, which is similar as face centered, and hence they have the approximate equal amount of packing fraction. Now what's important about packing fraction is that it helps us calculate the stability of the unit cell. So more the packing fraction, more is the stability, that is the 3D space occupied inside the unit cell, right? So in this way we can calculate it. Also there is one more thing, that let us see the contributions of the unit spheres inside the unit cell. So if we say that the unit cell is present at the corner, right? So the contribution that it will give is 1/8 only, because it's at the corner. So only 1/8 part of that sphere will be present, visible from inside the cube. If we talk about the edge, at the edge, since the edge is shared by 4 So it will be 1/4. How can you remember this? A very good point is, how do you remember this? For this we have a very simple idea. Yeah. So if I make cubes here, so this is a coordinate system, right? We have x-axis, y-axis and z-axis. On this I am trying to make some cubes. Simple. Let us make different cubes with different colors. Then there is one more cube down there, just behind it. Yeah, here. And then there is one more cube right next to it. Okay, right. There are 4 cubes, right? Exactly behind it we can say there are 4 more cubes. Yeah, one is there, the other is here. Now this is going to be a little cluttery, but stay with me. I'll show you a very simple way to remember all this. Now similarly 2 more behind it. Now as we talk about this point here at the center, right, this point is shared by how many cubes? So there are 1 2 3 4 in the front and 4 behind it. So at the corner it is shared by 8 different unit cells, hence the contribution is 1/8. But if you talk about an edge, any kind of edge, so this edge will be shared by only 1 2, right, at the top, and the other 2 at the bottom, 4 unit cells. So this edge is generally shared by 4 unit cells, hence the contribution is 1/4. Similarly, if we talk about a face, alright, so let's talk about this face. So this face is shared by 2 unit cells. So for a face centered we have a contribution of 1/2, whereas when it is inside the body, the contribution goes complete 1, right? So in this way we can calculate the coordination numbers of the, and once we calculate the coordination numbers we can go to packing fraction also. Okay, now once you have calculated the packing fraction, so can we just check some questions related to it, right? So if I say what kind of questions appear, let us talk about that. We have a lithium. Yeah, one more thing, simply. So here we have lithium that crystallizes as a face center, as a face centered unit cell, right? And we are given the density of it. So density is given to us. Now density is given to us as 105 gram per centimeter cube. Now what we want to calculate is edge length. Now what we know is here density is to mass upon volume. Okay, we have the density of the unit cell. What we want is edge length, mass of the crystal. Yeah. So what we do is we use the formula. So here this Z is basically the contribution of the unit cell, right? And the M will be the mass. We know the mass of the atom. If you're talking about lithium, we know about the atomic mass, right? So you can put that also. This is the density, okay, and this is the Avogadro number. Now if we use this kind of formula, we know the mass, we know density, we know what the Avogadro number is. There is a very constant number, it is 6.023 × 10⁻23, and then we have the coordination number. So if we multiply this, we get the volume. Once we get the volume, see, we are using the similar formula, we are not doing much. The formula is density is equals to mass upon volume, okay, but we are given volume, we are given density and we are given mass, we are not given volume. So if we find the volume out of the system, we can further find the edge length also, because volume simply will be a cube. So what we need to find is cube root of the volume, right? And hence we can calculate the edge length. But to calculate the volume, the problem basically lies is that the number of atoms that are present inside it, right? Hence we have to calculate, we have to multiply this mass by density with the number of spheres that are actually there inside the unit cell, as well as divided by the Avogadro number, right? If you use this kind of formula, we can directly find out the value of the edge length, right? Similarly, kind of questions that arises are about the packing fraction. So they directly will ask what is the packing fraction for any kind of unit cell they can give you. So they can also make up unit cells. So think about this one. So if this is one of a unit cell with atoms present here, right, that is the corners, and suppose there are atoms present at the edge. Yeah. So how many edges do we have? So these are 4 here, 4 here, and 4 at the corner. So basically 12 edges. 12 edges and 8 corners. The contribution for 8 corners will be 1/8, and for 12 edges the contribution will be 1/4. So total number of atoms present in the unit cell will be 4. Now this number will have to substitute to Z. So in similar ways they can even form new unit cells, or they can give you from the ones that you have already studied, right? Hence we can actually calculate the total number of atoms present in the unit cell. So talking about the hexagonal type, we are checking. So if we talk about the hexagonal type, so the atoms are present at the corner that we know. Then we know about the 3 atoms that are present at the center of the body, right, in the middle of the plane, and there are 2 more atoms that are placed at the face center. So for this reason, total number of atoms that we'll have will be 12 at the corners. Now for the hexagonal one, the corners will occupy only 1/6. Hence we have 2 from the corner, right? Then there are 3 at the body, inside the body, so they are complete. So their contribution is complete 3, and there are 2 which are present at the faces. So the contribution will be half for 2, that is overall 1. So hence the overall number is 6 here for the hexagonal unit cell. All right. Moving on. So basically when we talk about these kind of unit cells, so these unit cells can also form a lot of different kinds of packings in the crystalline structure. So let us study about those packings also. What kind of what kind of minerals, what kind of lattices will have what kind of packings. All right, let us check them. So talking about simply talking about the first structure, that is NaCl. Let us say NaCl. So NaCl has a AB type packing, that is there are two. Now there is a different thing. Now this is the ionic compound. Now what we were talking about in a unit cell were exactly same atoms present everywhere, but in an ionic compound the atoms are not same and they are not present basically they are not present equally throughout. So what happens is, for an ionic compound like this NaCl, the structure that it takes is simply like this. So we have an Na and then there is a Cl, correct? Then there is a Na and a Cl. Similarly another Na and a Cl. Now connected to this Na here, let us denote this with the Na plus and this with the Cl minus. So connected to this Na, on bottom of this and the top of this will be a Cl, even on the side, and connected to this Cl there are Na pluses. So do you see the alternate arrangement everywhere? And now consider this in a 3D structure. If you think about this in a 3D space, I'll represent it with the dots only. So I have this Na, so I have this Na and then there is Cl, NaCl, NaCl. Similarly, oops, so yeah, so now do you see, right? So these structures, we have alternate structures. Similarly behind, if we go, we find here Na, then Cl, then again Na, similarly we can go on top and bottom as well. I'll just form this whole unit. So now you'll be able to visualize how this NaCl should look like, right? So what happens is, so there are different types of system that are present in the unit cells. Let us see the different kind of systems. All right. So for NaCl, as we know, it's a face-centered unit cell, the most basic one. So what happens is, in the face-centered one, we'll have the structure to be AB type and the coordination number S4. Now, how do we calculate the coordination number for this one? Why is it not 8 and 4? Because for NaCl, the whole unit is made up of 2 atoms, right, which are different in nature. So in the crystal structures, when we see them, what will happen is the Cl minus will form a FCC arrangement and the Na plus will go and occupy the other sites which are available. Now what kind of sites are available when the structures are formed? So there are 2 major sites which are available. We call them octahedral and tetrahedral. Now how are they formed? Let us understand that. So we have a structure, right? We have a simple structure of a lattice. Let us talk about one plane only. So we have this plane where these structures are arranged like this. Right. So now, if do you see the system? There are 3, 1, 2 and 3, talking about these 3 atoms. Now if on the exactly on the top of it, if I put one more unit cell, another layer, right? Similarly like this and this. But if I put one more unit cell, so what will happen is that in between the two layers there will be a space which will be left inside. Now this space, when it is formed by putting atom on the three which are down below, the space that is created inside is called a tetrahedral void. What is a void? Void is basically simply a space, empty space, correct? Alright, so basically if you want to visualize this, we can talk about carbon and methane. So how is carbon exactly present in the methane? It's in the tetrahedral geometry, right? So all the corners are being occupied by hydrogen, and the corner, the center is being taken by the carbon atom. So it's similar in this case also. We have four different atoms, one on the top, three at the bottom. You see here also three at the bottom and one on the top, right? Four different atoms, and in between these four atoms, if we have a space where an atom can go inside, this space is called the tetrahedral void. Okay. Similarly, if you talk about the octahedral void, so you can see, look at this space again, this structure. So this is our first layer of atoms, right? So what I can do is, here is this first layer. Abhi, if I put another layer such that the void of the first layer and the void of the second layer are exactly on top of each other, how will that be? So in this case, the atom will not come exactly above the void, but what will happen is there will be another layer where atoms will be present like this. So do you see this void again? Now there are two voids from top to the bottom. So there will be a bigger void inside it. If I show you a side by side arrangement, how will it look? Here we have three different atoms, right, on the top, and the bottom will have a different set of three different atoms. Now this space and this space, when they actually come on top of each other, so this kind of void is known as a octahedral void. If I simply make the structure about this one, it would be like this. So this void at the center is known as a octahedral void. So these kind of voids are majorly possible. One is tetrahedral and one is octahedral void. So in FCC the NaCl structure, so Cl- takes the face centered. So when we say that Cl- takes the corner in the face centered structure, that is, here I have the atom. So all the corners will be covered by Cl- now, right? And the faces, the center of the faces, they will be covered by Na. Like the ones here, right? So in this type of structure, the sites which are covered with the Na plus are the octahedral sites. So when we talk about the octahedral sites, they are present here in this system, right? So here we have again a Cl-, a Cl-, a Cl- here, Cl- behind, and Cl- at the center here, top, and a bottom, right? So all the face centered sites are covered by Cl-. Now this face centered geometry will create us octahedral sites. So these octahedral sites are majorly present at the edge. So these edges are then covered by Cl-. And also there is one at the center, body center. So these are all the octahedral sites. Similarly, if you talk about a cesium chloride type arrangement, there is also an AB kind of structure, right? We have one cesium and one chloride. So in this one, this is majorly a body centered kind of arrangement. It is a type of the arrangement. It is not exactly that. Why? Because those were the unit cells which contain only one single type of atom. But here we have more than one atoms inside the unit cell, right? So the type will be FCC or the BCC, but they are not exactly the same. Getting the difference? For a FCC unit cell, all the atoms have to be same. So it can be only this type of structure. So if we talk about cesium chloride, so the cesium chloride in this form, the chlorides are present at the as a simple cubic arrangement. So simple cubic looks like this. So there are 8 chlorides which are present at the corners, and the cesium will take the body center, just the body center. Yes, here, being big in nature, cesium will take the center of the body, right? Now in the NaCl kind of structure, when we talk about the coordination number, so when we calculate how many atoms are present inside the cell, what we talk about is, we talk about the chloride atoms differently and we talk about the Na atoms differently. Why? Because they are two different kind of atoms in the ionic compound, and both are necessary to form that ionic compound. Otherwise the compound will not be called a salt, NaCl, right? So both are necessary. So hence we can calculate it, and what we get is, for the coordination number, for the face center chloride, obviously it will be 4. We have calculated before, right, for the chloride. And for Na plus, we can see, so there are 12 edges with 1/4 contribution, right? So 12 edges with 1/4 contribution will give us 3, plus 1 is present at the center, which is complete. So again 4. So 4 chloride and 4 sodium ions are present inside one NaCl crystal, right? But coordination, if you talk about the coordination number, right? So the coordination number is the number, the kind of the types of atoms which are exactly consecutive to the R1 atom, right here. So if I talk about the Cl minus, so the types of atoms are present just beside it, touching it, will be one behind it, one in front of it, one on the left, the other on the right, one on the top, and the other on the bottom. Total how many? 1, 2, 3, 4, 5, 6. So the coordination number goes to 6. Similarly for Na plus also, the coordination number is 6. So as many atoms that touch Cl minus will be 6 Na plus atoms, and as many atoms that will touch Na plus will be 6 Cl minus. Hence the coordination number comes out different for each. Okay. So if we talk about the Cs plus CsCl kind of structure, so here now we can see that this Cs is touching all the 8 chlorine minus. So the coordination number for Cs plus will be 8. But what about the chlorines? How many cesium are they touching? So 1 is touching here, right? But similarly on any given corner we can make 8 cubes, as we just learnt, right? So if we talk about this one here, this one is touching one down below, behind, so 4 at the bottom layer and 4 similarly at the top layer. So total how many? Cl minus, again 8. Hence the coordination numbers, the way they are touching each other, is 8. But the contribution of atoms that are present inside the unit cell, how many? So CS1, so we're talking about just one, the contribution will be 1 at the body center, Cs plus, and Cl minus again, because they are present at the corner, 1 again. Alright, and since they both combine together to form one molecule, so only one formula unit is present in the unit cell. For the sodium chloride, only 4 formula units are present inside the sodium chloride unit cell. Okay. Lastly, let us talk about the short defects, the kind of defects that are present. So there are two types of defects that you need to remember. One is Schottky and one is Frenkel defect. Now, there is no such thing as a perfect crystal. There is no such thing as perfect crystal. Kindly remember this. Why? Because it's very important. A perfect crystal will be no use to us. So the defects are actually very important, as they allow the passing of electricity and everything. The properties that are shown by the crystals are due to the defects only. Now let us learn what is Schottky and what is Frenkel. So if we have, let us say, a system like this. Now, if in such a kind of system, a pair of ions, positive and negative, comes out, I am blanking them with this green color. Let's say this atom, a positive, and this negative atom are no more there. So now how will the system look like? Right? So one blank here and one blank here. So when a pair actually leaves the whole atom, so this kind of defect is known as a Schottky defect. But now there are times when atoms are actually big and small, right? They can be big, they can be small, they can be of any size. So here, now what happens is, in a Frenkel defect is an interstitial defect. What happens is, this atom is so small that it can travel inside the whole lattice structure. So it loses its space from here and goes and sits here. Now that is not his correct space, but still he is living there. And hence, this kind of defects, when the atom is not present at the correct space but somewhere inside the system, they have not left the system. So this is known as a Frenkel defect. Alright, and this is known as a Schottky defect. One important compound that I will tell you about before leaving is AgCl. Now this AgCl, this is a question which is frequently asked in all the competitive kind of exams. They ask you what kind of defect does AgCl show. Now you choose a Schottky or a Frenkel, but no. AgCl is a compound which is able to show both Schottky and both Frenkel defects. Hence this question is quite important and need to remember, right? So more about this we'll talk about in the next classes. Thank you for now. Thank you.